We don't have PDF copy, sir. If you have, please share with us.
PDF, I think PDF is not required, no? Is it required for PDF? No, in your library, I think you have. Let me see if I have it here. Children, I don't have. Okay, I'll try to download and send you, but it's available. I'm not sure it's available. Okay, so just a minute.
Sir, I have one book, sir, Alexander Corin, A Mathematical Introduction to Fluid Mechanics, sir.
No, not that one. I think your textbook is basically Choltran. Fluid Dynamics by F. Choltran. Okay, so we'll see. Wait. It must be there in your library.
Yes, sir. We have to search, sir. If it's,
Okay.
it's in library.
Yeah, it must be there. Let me a minute. CHO Charlton. CHORLTON F. Charlton F. Yeah, we have actually. So there is a textbook of dynamics. No, not that one. Textbook, fluid dynamics textbook is required. So let me see if it's available online. We can download. Charlton F. Viscous and compressible fluid dynamics. Yeah, this is what is actually required. So I'll download and viscous and compressible fluid dynamics. Okay, that must be the half middle. See, actual textbook is like Indian edition you have. That involves whatever we have done so far plus viscous equations. It's equations and then solutions of Navier-Stokes. Okay, so the same fellow along with somebody, he has written two books. One is for incompressible and another one is for compressible. I think what we are doing right now is compressible. Okay, so only if I download only I can tell whether it is that or not. Okay, so we'll start anyway. So we'll see. I think I'm able to download right now that one. But I don't have incompressible fluid dynamics. Better if you get incompressible fluid dynamics. Everybody join.
Sir, 5 are there. 5 total. Yes, sir.
I think that incompressible part is not there. Hello? Yes? Hello? Yes? Actually கிளாஸ்ல இருக்கேன் நீங்க 7:30க்கு அப்புறம் ஸ்டார்ட் பண்ணிட்டு வரீங்களா? ஆமா, another 1 hour எனக்கு இது இங்கதான் ஆகும். இதுதான் சொல்றேன். ஆல்ரெடி இன்ஃபார்ம் பண்ணிட்டேன். பரவாயில்ல, 7:30 8க்குள்ள வர்றது மாதிரி பரவாயில்ல. I'll try maximum 8 o'clock அங்க இருப்பேன் நான். Thank you. Hello, sir. Driver 255. Okay, so anyway, I think that first book is not available. After downloading, we will see whether whatever we are teaching here is available in this textbook. Okay. So today we'll try to finish this and get the equation, the Navier-Stokes equation today. Okay, so that's the aim. With that aim, let's start. Whatever I showed you yesterday, I'll just try to write it for you. So look at the notes, whatever you have. Whatever you have, that notes I sent you, no? That notes, page number 19. If you are interested, just keep it open and see. If you don't have, just leave. I'm just using the same thing. Okay. So if I write it, I think it's easy, no? See, so far what we're doing is we're trying to get tau x, tau y, tau xx, tau yy, tau zz in terms of elastic components. But what we got is tau xx, tau yy equal to but see, x dash y dash coordinate system left side, right side is basically tau yx, which we already know. It is given in terms of the deformation. This we already in terms of deformation. So in the xy coordinate system, gamma, right? This is your gamma yx or xy. Okay. So because we are writing tau yx is same as tau xy, so gamma yx we are writing there. So that is the deformation because of this force. This stress tensor tau yx. So we are going to now relate this one. The right hand side is given in terms of linear. So what is this one actually? So this is the angular deformation, rate of angular strain, right? This is the linear strain. It's like, a translation. Linear strain is basically translation. Angular strain is a kind of rotation. Okay. In xy coordinate system.
Yes, sir. What is angular strain, sir?
Rate of basically strain only, I'm saying. Rate of, okay, so it's not angular. See, yeah, angular is like, okay. I have to, let me show you what it is. Okay, now it is downloaded. Let me see whether that book, let me see how, whether whatever I'm teaching is available there. So that it's easy for you. Okay, see, angular strain is because of the rotation. See, because of these stresses, there is a what happens is there is a strain means what? There is a displacement in the fluid, right? See, the square becomes some kind of parallelogram, right? That's a parallelogram. So it is, that is where whatever that is actually angular strain, rate of strain in the xy coordinate system. This is gamma yx is basically angular strain. Okay, so what I'm trying to do here is this one. Okay, let me write it. So what is this one? Is this becomes this one, right? See, this is converted to this. So what happens? This is basically changing. No, this is the angular, right? The displacement that is changed, right? This is basically, this is your gamma x, right? Gamma yx is basically this one, and here also this side it is also lifting, no? So basically it should be like this. So this is the one. This is this portion plus this portion is basically gamma yx. Okay, so why should it be this square can also go a little bit this side also, right? So this is the original one. Let me write. Okay, so this converges to, this becomes same size, but instead of earlier it was here. Okay, now it is here. Okay, so this is a t. So basically this is a t and this is a t plus delta t. So this along the x direction, along the y direction, along the z direction, it is simple translations are linear strain. Linear strain. Are you understanding? This is basically is because of the rotations are taking place, basically, right? See, it is deforming, no?
Yes, sir.
The fluid element is deforming. So there's some kind of rotation here. Because of that this is called angular strain. This is the difference. So whatever that gamma yx, if you actually see, look back and see, gamma yx in the xy coordinate system is basically angular strain. So this is what you see. You might have got it that gamma yx here like this from this figure. Now we are looking at only this one. So that's what we are going to do it. Okay, because this is related with this one in the x dash y dash, because in the xy coordinates rotation is same as you are seeing in the x dash and y dash. Already you rotated, no? The coordinate system is already rotated. So after once you rotate the coordinate system, and whatever the deformation is basically linear deformation. Okay, so without rotating, basically what you are getting is angular rotation, angular deformation. That is what is gamma yx. Okay, you understand now? See,
Yes, sir.
simple. This is simple translation. Simple translation. This is some kind of rotation due to rotation. Okay, rotational effect. This is translation effect. That's what it means. Okay, so I'll leave it like this. So this is what we are going to relate now. So once you relate this one, then everything will be x dash y dash. Left hand side is already x dash y dash system. Now right hand side, if you relate with this, this is a now d epsilon x dash. Okay, this is a linear strains in the x dash y dash direction. If you actually relate, then we are done. So everything in the dash dash x dash y dash system. So we can drop the dashes. Okay, so that's what we do. I showed you yesterday the same thing. So for that, you look at this square, the square that we have ABCD. Okay, so at time t, in this you take ABD. Okay, so this time in this here, this I'm making it. I'm looking at it as ABD. ABD. So this is your. I'm trying to look at this triangle as ABD. So this ABD, this is at time t. So after time t plus d, what happens? This becomes this, and this becomes, this rotates to this. This is this one. So this is how it is becoming. Okay. So in between exactly you have x-axis, x dash, and this is your x-axis. This is your y. Okay. So this extra length that you have now, this one, this is your A, and this is your B, and here there is a translation here is happening, that is at C, and then you're going at this length is D. Okay, do you understand what is happening? This triangle is becoming like this.
Yes, sir. Sir, why they is is fixed like from perpendicular and to base both sides, like compress, sir?
Huh?
Why they compress after T, sir? Like from perpendicular side also and from base side also, sir.
No, this is also moving. A is also moving. But see, finally, what you are saying is, you look at this one. This is what? This square becomes parallelogram after moving. So that
Yes.
translation along the x-axis, if you consider, that is exactly your C here, your B here. B is not B. Along the y direction, A length, it goes up in the y direction, and B is like a rotation. It just rotates with the distance, this much distance. Similarly here, it translates up to C distance, and then it rotates up to D distance. This is the new ABD. Okay, this is your ABD new at T. This is at ABD, same ABD at T plus delta T. This ABD at T. You understand? So shall I show you that file there? You will understand immediately.
Yes, sir.
Maybe I'll show from here. So can you see now? See that ABD originally it is at time t. You see? Do you see t here?
So we can't see your current file, sir.
What are you saying right now?
The notepad, sir.
Wait. I think yesterday it worked. If I share it. Oh, I didn't. Wait. Entire screen. Hello. Okay, now you can see. See, can you see that one now?
Yes, sir.
Yeah, you see this. This now I'm taking ABD and ACD. ACD. Okay, ABD and ACD triangles. If you take, why I'm taking ABD and ACD is because AC is in your X dash direction, and then BD is in your Y dash direction. That for that reason I'm considering these triangles instead of by looking at this full square. Instead of looking at the full square, I take half this. I mean ABD and ACD. The reason is AC and BD are basically your X dash and Y dash. In that direction, what is the change I'm looking for? You understand? So similarly, you see this one. So ABD. So already we mentioned AB. Same AB is going to be here, but here it is going to be CD. Now I have a C. This C edge is the right C vertex for ABCD square. Here you have this will become AD, A plus D. This is the distance A. It will go move. Already this distance D, A plus D along the Y direction, and then X direction. Already C here in the first triangle, and here angularly B distance it moved angularly. So that together is B plus C. Okay. Is it okay?
Yes, sir.
So that is one. So you're writing both. Okay. So now you look at what is the change in the along the X direction. So let's calculate what is the change that you see. Okay. If you understand now, if you look at this equation number 27, what is that you are writing there? What is equation 27? Change in the XY coordinate system. Change. I mean the deformation, a linear deformation. Okay, this is basically linear deformation, or basically deformation or linear strain. Okay, linear strain deformation change. What is the linear deformation change? What is the deformation that you get here? So basically d epsilon x, if you call it, along the X direction, in X direction. D epsilon is what? What is the distance that it moved translated? ABCD? C, right?
Yes, sir.
That small c. See, this small c is the only thing translated. So c divided by, so everything is like h. H is the length, square, right? So c by h is this one. Similarly,
please share your notepad notes, sir.
no, I'm just writing only the 27. Okay.
Okay, sir.
27 only I'm saying. So d epsilon y equal to, now what is d epsilon y equal to? A by h. Why A by h? Because it is moving in the translated only in the, see, look at ABD. It is translating in the Y direction. That is only A distance, that small A distance, divided by that h. You understand?
Yes, sir.
Okay. Now what is the third one? If you write, what is this deformation? Angular deformation. So angular deformation, this is a change in the angular deformation. Angular deformation in XY. It happens in the XY plane, right? Deformation both sides it takes, right? Not only this C, I mean, of course, for the triangle only I'm talking, okay? In Y direction, for these are for ABD triangle, okay? So triangle ABD. You understand? So if you look at this ABD, I can only get whatever translation. If you see, those are in the X direction and Y direction, and the rotation that is happening, B distance and D distance, right? That is actually angular deformation in the XY planes for triangle ABD. So this is going to be gamma XY equal to, how much is that? What is that? B plus D, right? So you're going to get B plus D divided by H. So that is the change divided by H only, right?
Yes, sir.
Yeah, that's all. That's all. So that's what is exactly your 27. You understand? So if you consider ABD, you get only in the XY plane only you get. So now you consider ACD triangle. If you consider this triangle, that you simply look at that second this one. So ACD. Okay, this is your ACD. And then after moving, what happens? This moves this side. So this is your A and B. Okay, A and B. This is the translated y direction is A and rotation is B. Okay, that is same. And then what happens here? So because of this left hand side here also, this move to some distance. It's like this, right? So what is this distance? This difference. So this is actually coming because of this is actually your C. This is your ABCD. Okay, A, I mean this is A and this is D. Actually you have a B here. Okay, so because of this, whatever ABC, whatever is happening at the B translation in the first triangle here. Okay, that effect is you see here as C plus B plus C here, this much distance, and here what is this distance will be A plus D. Can you see that one? A is moved y direction, and here D is also moved in the y direction, right? So that together is happening here. Can you see this here where my cursor is? A plus D. Similarly, B plus C is deformation along the x-axis here in the first triangle, and then C is just translation. B is translated to C. So B plus C is going to be this much distance. You understand? So this is at time t plus delta t, and this is at time usual. This is at time t. So if you consider this one, okay, I'm looking at only x direction, x dash direction, and y dash direction. So now I'll try to write. If you write deformation, so linear deformation along x dash direction for triangle ACD. If you look at this one, what is that you get? So what is that I'm asking? D epsilon x dash, right? That is along the AC. So that is same as change in this piece AC divided by actually AC, right? That's what you are seeing there, 28, right? Maybe I'll show you this one now. Maybe that is the better way. What is that I have to show? Stop sharing. Now can you see this one now? Yeah, see I'm writing the same thing whatever is there. So this is going to be D, see change in AC. This is what is the change in AC divided by AC. AC is how much? We don't know, right? So what is AC? This is H and this is H. So this is going to be root 2H, right? So denominator root 2H. So what you have, what is the change here? So this is the change. This distance, if you want, this you project it. So B plus C, you project it onto the hypotenuse at 45 degrees. This is also 45. A plus D is also, you project it onto 45 degrees. That way, if you look at it, it's going to be A plus D divided by root 2 plus B plus C divided by root 2. So this also you can think of the same way. So hey, why should I see this triangle, this right angle triangle also? You can think of H you projected onto this one plus another H you projected onto the hypotenuse. You get the same number. Okay. So like above, denominator also you can put the same way. So both are same. Followed?
Yes, sir. Yes,
So
sir.
now I am going to just rewrite what it is. Okay. So that one, whatever we have right now. Yeah. So D epsilon x dash. This is the linear deformation along in the x dash direction. So basically, the x dash in that x dash direction, what is that you get now? I'm going to just rewrite. So root 2, this root 2 come down, so it's going to be half divided by h. Okay, so I take c here, so c by h I write here, whatever we just looked at now, and then you have a by h, and then whatever is left you write it. So here b plus d divided by h. Can you see that one? So what is this one? This we already just calculated, no? So this is actually d epsilon in the x direction plus d, I mean the linear deformation in the x and y direction plus angular deformation in the xy plane. That is your xy, gamma xy. This is your gamma xy, right? Both the xy plane that we are considering, right? So you consider both actually for the full square. This is for full square, for square ABCD. Okay. So if you write like that, that is what we got. So do the same thing now for along the y direction. Okay. Similarly, in y dash direction. So what is that you do in the y dash direction?
Just to calculate the change, sir, in all directions, like d epsilon
But
y.
no. To do that one, what are the triangles that you need to take? Yeah. What is that you get?
BCD and ABC.
ABD. Actually, ABD itself you're seeing, no? So along the BD, capital B, capital D. Okay, in that direction you are looking at it. So we'll just write it and you will see. Okay. So here also, if you actually ask for this one, you will get d epsilon y dash. In the same way, same way you will get deformation in the. Let me see exactly what it is. Yeah, same you will get. Okay. So why you get this one, I'll tell you. So this one plus d epsilon y minus, you'll get a minus sign here. Can you see why it is? BD, ABD triangle, you have to look at it. Now, ABD, okay? Consider, by considering triangle ABD. Okay? So that we already have now. So something like this. This is your ABD. So after this, moving, then this is what you will get. This is what it becomes, and this one. So you'll have CD. This is your C, and this is your D. Okay, this is your A, and this is the distance it moved. This is what it becomes ABD now. Okay, after this is at time t plus delta t. This is at time t. Do you understand what I'm doing? So here you see that it is reduced, no? So it is reduced. So overall, you'll have to write neatly that just to understand exactly how much. So I think you take it as a challenge and try to see why you get this minus sign. The same way, okay? I think you will follow if you understand. So basically, there is nothing. So now geometry is basically okay. So what is that you're seeing? Basically, you have to minus it, right? Something you're minusing. What is that you're minusing? B plus D only or minusing? Okay, it's reduced, no? Isn't it? Hello? Here also it is increased, right?
Yes, sir.
See, AB, no? AB is here. So here you don't have to do like here A plus D, B plus D. Here, what is reduced here is somehow you can just think of it, okay? So you can do it. Work with ABD and you get this negative thing, okay? So this you verify, okay? That's you can easily see. So same way. So exactly same way. Follow the same way. Okay, so you verify this one. So now you have got together. So now you take the difference. So this implies d epsilon x dash minus d epsilon y dash equal to, what is that? This part will go, no? So half d gamma xy minus minus plus. So it is going to be another half d gamma. So this finally d gamma xy. Divide with dt both sides. What you are getting is d epsilon x dash by dt. So rate of change, rate of strain. This is your rate of strain. Okay. Rate of strains, rate of linear strain. And along the x direction, and this is the rate of strain in the y dash direction equal to, this is the rate of strain angular. Okay. Rate of angular strain in the xy plane for that square basically. So this is what you got. Okay. So once you get this one, now you go and substitute there. What is that you have? You already got tau x dash minus tau y dash equal to 2 times mu into d gamma xy by dt. This is what we derived yesterday, ending. You see this here, this one, and this one. I'm just writing the same thing. So, okay. So once you write this one, now you got your, what is your d gamma xy. So that is equal to 2 mu times d epsilon x dash by dt minus d epsilon y dash by dt. Okay. See, now you see this left hand side and right hand side, everything in terms of x dash y dash. So coordinate system changing will not change anything, no? So this implies you can drop dashes. So that what you are getting is tau xx minus tau yy equal to 2 mu times whatever you want you are getting, no? So this is actually d epsilon x by dt minus d epsilon y by dt. So epsilon y, epsilon x are basically linear strains. Okay, linear deformation. So now we need to calculate what is my ddt of epsilon x, right? Still I'm not done. So now to see this one, so I'm just writing d epsilon x. Yeah.
These two equation what saying, so like in whatever coordinate system we will select, they will always same. There is no.
Yeah, if you see, for example, if you have see, you rotated the coordinate system. Suppose everything in terms of x dash y dash. Now you drop it. It is like its rotation. Rotation will not change, no effect. Coordinate system. See, I'll put in. You have a fluid. Something is happening. You already calculated in a in rotational coordinate system. That is same, you know. By just rotation, it will not change, no, physically, right? Mathematically also it is the same. So you can drop always, provided everything should be in that coordinate system. So right now, if you see left hand side and right hand side, okay, this one and this one, both are in the x dash y dash only, no? Isn't it?
Yes,
Look
sir,
at
yes,
this,
sir.
this and this one and this one. If you look at everything in the x dash y dash, so I'm dropping dashes so that this is in the xy coordinate system, right? But still I don't know what is my ddt of linear strain. So that linear strain, I'm now, what is the linear strain that I'm asking? I told you, no. So this, if you do, this becomes just some small translation happens. What is the translation happens? It moved this distance it moved along the x direction, and this distance it moved y direction, right? So this is actually your, what is the value that you get?
So just simple in transformation did
So
epsilon x.
you assume that this is your delta x and this is your delta y. Okay.
Yes, sir.
So this is actually, this will be okay. So I don't say exactly this much. Okay. So actually originally this much. Okay. Originally this one, whatever this small thing, you know, this is actually the rate of d of delta x. That is the change. Okay. So similarly here, where is the y? Y is what? This is the original. This is the extra this way, and this distance. This distance is delta y rate of change. Okay. So what is this one? For example, d of delta x is actually that velocity, no? So that is in this x direction. What is the velocity component? Dou u, no? So dou u by dou x, right? Dou u by dou x into delta x, right?
Yes, sir.
Actually, okay. So don't write anything here. So simply write du. Okay. So the distance is basically because of u into this is a velocity, right? Small velocity into dt, right?
Yes, sir.
So then it is this is the distance it moved, right? This is the distance it moved. Now I'm just dividing with dou x, dx and dx. Okay. So dou u by dou x, you know. So that is what it is. Similarly here, this rate of change in the y is basically dou v by dou y into dy, I mean delta y. If you want to write delta y or delta x, that is okay. So dy into dt. Okay. So this velocity into dt is basically the distance. Dy cancels. So that is basically this rate of change, no? That is the distance, right? So what happens? This d epsilon x will be equal to. So I'm just writing. What shall I write?
Sir, that small changes due to velocity only, sir.
Huh?
That small changes d of delta x, sir, due to velocity component.
Yeah, ddt. So you divide, no? So now if you divide by dt, this divide by dt, this will go. Okay. So you just write the same thing. So what happens to dx? Delta x dou v by dou x to delta x. I think we are losing time. So basically what you are getting is, so this is going to be equal to dou u by dou x into dt. Can you see this one? Dou u by dou x into dt. Dt gets cancelled, right? So yeah, that's okay. So we are writing, let us see, without, let's not divide it first. Okay. So if I put it like dt here, yeah, can you see this now? Okay,
Yes,
so
sir.
okay, I'll tell you why it is. You remove this also. Now you agree? Dou u into dt, right? That is the distance. That is the change in the translation, right? You write
Yes,
here.
sir.
Du dt, you write here. That is the change, right?
I am asking why that small one is du dt, not complete change du into dt,
Delta
sir.
u, simply write delta u, delta t. Finally, you are going to take delta u, delta x will go, no? So you here also you write like what is the change here is basically dv into dt. I am writing dv means not basically delta, okay? Small delta. If you put it, both are same only, okay? You don't look at that way. So finally, when you take delta t goes to 0, there delta x, delta y also becoming very, very small, right? And delta x, delta y goes to 0, finally you will get it at point.
Yes,
So
sir. Yes.
you see this one. What is the
Well,
change that you do? Change here is basically like earlier, change in the translation, linear strain divided by what is that actually originally this is your delta x, no? That is what is your delta x, right? This is what is the dx. Delta x is basically dx. I'm writing dx here. You understand?
sir,
Similarly,
I am
d epsilon
asking.
y is dv dt is the distance, that is the change divided by originally how much is this is your delta y, no? So dy.
Yes, sir. Yes, sir.
That's what. So these two now implies
Sir, I have one doubt, sir.
Yeah, d epsilon, 1 minute, d epsilon by dt equal to du by dx, and d epsilon y by dt equal to dv by, that is your, these are, what is your u and v? Velocity components. V and u are basically velocity components. Okay. Yeah, tell me, ask me your question now.
Uh, Sir, like there is a deformation, simple linear transformation, sir. Why, whatever deformation we got, sir, why there is two parts, sir? Like one small part, dx, d delta x, and some other part also, sir. Why we not consider whole is there some deformation like
Because
delta?
see, because I'll tell you one, there are two things are happening. One is the linear deformation, another one is angular deformation. So you got
But in
the
this, in this case, only linear deformation is now.
yeah, we want now finally what you got here. So I got finally when you drop the dashes, I got the stresses are connected with still linear strains, no? Now I need to connect this thing with velocities. That is easy. That is what we are doing now. See, so far you are here, right? Now I don't know what is my epsilon x, epsilon y, right? Rate
Yes,
of change of epsilon x, epsilon y, I don't know. That is what
yes,
I'm trying to calculate. Those
yes.
are actually linear strains. So if you, that is basically translations. Translation, if you look at it, what exactly d epsilon x? That is
Yes,
simply
sir.
du
That one,
dt divided by dx.
yes, so
And
that
basically you write delta u dt, delta u delta t divided by delta x. And finally you take delta x goes to 0. That is what becomes finally dou u by dou x into dt. So dt, you bring it this side, d epsilon x divided by dt equal to dou u by dou x. Similarly this one. So what is this one? This is actually capital D. So both are same, no?
yes, sir. I am asking that, sir. I understood this equation, sir. Why this translation comes in two parts, sir? Like one is like you underlined this one, this simple transformation, sir.
Where is the
Why
translation that I did?
no,
Earlier,
sir,
you mean this one? This one? Two different triangles you are saying?
no, sir. Last one that linear deformation, sir. Simple linear deformation. Last
Yeah.
one, sir.
Okay.
Why,
Last one. This figure
yes,
only
sir.
you are interested. Yeah. Tell me.
Yes. So here you consider two parts, like this is the delta x, this is the delta y. If we here is the linear deformation, why we consider
See,
two parts, sir?
okay, I'll tell you. See, basically, what is happening? This delta, this square, it moves to little bit here. If it moves like this, so okay. See, just to understand, I'm just writing initially it is here, right? When after some time this becomes a little bigger. You understand? This
Yes,
becomes
sir.
a little bigger, but still it is square. It
Yes,
moved. So
yes,
you understand whatever this earlier original this thing, you remove it. Okay. So this is the extra translated and this is the extra translated. That is what we are trying to get it. Those are, so which
okay,
direction? This is x direction, this is y direction.
okay,
That is
sir. Now
what I
I got
want
it.
now.
Yes, yes,
Yeah.
I got it, sir. Yes,
So
sir.
that is why we are doing both sides, both this side and that side. D epsilon x and d, because that's what we need, no? So now go and substitute into finally your d epsilon is, so if you come and substitute here in this tau xx, I'm writing now completely next slide. Tau xx minus tau yy equal to, what is that you are writing here, equal to 2 mu. Now those rate of change of linear strains are now I know. So that is simply dou u by dou x minus dou v by dou y, right? So this is only for one face, right? One square in the xy plane. You have a full cuboid, right? That's a cube. So if you try to do the similarly in the xz plane, xz cube, xz square, if you take it, you will have tau xx minus tau zz equal to same mu, because mu, that is the assumption. Okay. So this mu is same because this is the viscosity in all direction is same. That is the assumption. So what is that now you have here? So x means dou u by dou x. So you'll have a dou u, and you will have whatever here, dou u by dou x, right? Dou u by
Yes,
dou
sir.
x, and here dou w by dou z.
Yes, sir.
Yeah, this is what you got. So these two equations. Now you add it. If you add, what will happen? If I add this, I will get tau xx, 2 tau xx minus tau yy minus tau zz equal to, what is that you get? 2 mu.
2 mu.
Yeah.
Sir, 2
Dou u
that
by dou x
2
minus
into
dou v by dou y plus 2 mu dou u by dou x minus dou w by dou z. Okay. So now I'm trying to do something tricky. Just check it. Okay. So what I'm doing is I add and subtract something. So I add tau xx here and I subtract tau xx here. So what will happen? Then I will get tau xx, 3 tau xx equal to tau xx plus tau yy plus tau zz. Okay. Of course, this 3 I can divide. So divide by 3. Now what happens to, I bring it to the other side. Okay. So now this whole thing I will have to write now. So this is going to be 2 mu. Okay. So, okay. So, yeah, what is that you want to do? I want to do minus. This is minus and this is minus, right? So I want to write minus terms separately and plus terms separately, right? Dou u by dou x, dou u by dou x. That is anyway 2, right? And here minus 2 mu dou v by dou y minus plus dou w by dou z. Minus signs, no? Now here I am going to add dou u by dou x. Okay. So if I add means what? What is that I did?
sir, here is also sir divided by 1 by
So
3.
if I added here means basically I subtracted minus dou u by dou x. So I'll have to add here, right? Isn't it? Plus another dou u by dou x. Isn't it? That's what I did, no? So there is a minus sign here, I added. So there is a plus sign here, I again only added here.
Yes, sir.
Okay?
Sir, I am saying that there is 1 by 3 also, sir, in division.
Yeah, that is there. 2 by 3, 2 by 3. Okay, that you don't worry. So now I'll write it. I'm writing one more step. So this is going to be, so this is your tau xx plus tau yy plus tau zz divided by 3. And now you look at this one. This becomes what? 3 times this one, 3 goes. So you'll have a 2 mu dou u by dou x minus, now what happens here? 2 by 3 mu. Okay, 2 by 3 mu. Here, this is, what is this one? Dou u by dou x plus dou v by dou y. That is simply del dot u, your velocity component. Okay, so your velocity vector. So finally, what is that you get is this normal stress. Okay, so x direction, x component of the x direction, tau xx is equal to this is called mechanical pressure. Okay, so PM is this one. If you define this one, PM is this plus 2 mu dou u by dou x minus 2 by 3 mu. Mu is the viscosity, and you have del dot u. So where mu is, where PM is minus tau xx plus tau yy plus tau zz divided by 3. Okay, so this is called mechanical pressure. I'll tell you what to do. So what is actually happening here. So that is called mechanical pressure. You understand, right? That's the definition. Okay, so where this is called mechanical pressure. So don't worry about actual pressure is the one that will bring it out. Okay. So this whatever we are calling tau xx, tau x, yy, normal components, right? All normal components, stresses, those forces, we are calling it as mechanical pressure. Now what we do is, if you now try to combine it, okay? Are you following?
Sir.
Yes. Are you following?
Yes, sir. So what
Yeah.
is the use here to come like bringing one new term mechanical pressure, sir?
Which one? Mechanical pressure.
Yes, sir.
We'll come to that because you see there is something physics here. See, that is the problem. The problem that whatever you are doing right now is for both. We are not restricting to compressible or incompressible fluid. This works for compressible fluid also. So there is somewhere something called, once you do these adjusting terms, there is still not known. It's only empirically you bring out some other constant that is called that is also dimensionally that is similar to viscosity mu. Okay, so that if you bring it, that actually changes, right? Every time. Once you bring it, that will change. So that changes with time. So that becomes unknown there. So for compressible fluids, the viscosity is actually changing. So that itself become unknown. Once it is changing, no, see, rho is fixed for your fluid, isn't it? But pressure is changing everywhere. So similarly here, that's what we do. Okay. You just follow the logic. You don't ask right now. So okay. So I'm trying to define this. We were calling mechanical pressure. So now you do for x, y, everything you do. Okay. X, y, everything if you do, what is the value now? I 1 minute. Y I is dv by dx 2 mu. Okay. See, now I try to do this way. So now you know tau xy is, you know, right? Okay. Now I'm forced to write tau. Okay. Xy. What is tau xy? You already know mu into dou. Yeah. Dou u by dou y plus dou v by dou x, right? You already calculated earlier. If x is not xy,
Yes,
xz
yes.
and yz, right? All those things you know, right? Now can I combine these two? So if I write like this, you will understand. So exactly now I'm writing whatever there. So instead of xy, I'm writing I comma j. I is x, y is this one. Okay. So if I use this notation, I will have to write u bar as u1, u2, u3. Okay. So tau ij, if I put it as if you combine like this, so I'm going to write this one xx term. Okay. So that is going to be minus pm and then so what happens to this one? Okay. So yeah, minus this is going to be plus the first term and last term in this. Okay. If you write it, so this is going to be 2 by 3 times mu times del dot u. Okay. And this one into delta ij. Suppose I equal to j. This is what you are getting, no? Plus what, like here, if you add it, for example, mu times dou ui by dou xj plus dou uj by dou xi. Can you see now? If I take I equal to j, what is this term becomes? 2 mu into dou u by dou x only, no?
Yes, sir.
Yes. So
Yes,
that is
sir.
what we already have here, tau xx if you want. Now
Sir,
tau x,
how this delta ij comes, sir?
there is just a notational thing. So delta ij is nothing but equal to 0 if I is not equal to j, 1
Okay.
if I equal to I.
Okay, sir.
That is this is just the usual delta, Kronecker delta. Okay, Kronecker. Okay, so the advantage is that now I can write all tau ij. Okay, so if you put this one, now we can rewrite. Okay, now that I am going to do something different here. So I am going to write actually your P experimentally it is actually shown. Okay, so empirical. So empirically it is known that this is physics. Okay, so this is basically coming from experiments, not really theoretical. That is why it is not in your syllabus. You don't do compressible things. Okay, if you are doing compressible things, basically this mechanical pressure, okay, plus you add something else is adding. So because of this is coming from physics, del dot u. Because of this, what is the del dot u bar? This del dot u bar equal to P. So this is actually your P is your pressure function, usual pressure. Okay, so P is actually pressure. You understand? Where P is the pressure, actual pressure is the pressure at. This is the so where C lambda has same dimension as mu. It's called second coefficient of viscosity. Okay, you understand? So you just try to read that page number 24. Okay, so you'll understand that's just physics. Okay, so once you have this, now we go and put it into the equations of motion. What is the equation of motion that you got? Hello?
Navier-Stokes, sir?
Yeah, Navier-Stokes equation now that you got. No, not
Yes,
yet.
sir.
So now you have equation of motion is what? Equation of motion is, what is the equation of motion now? Where is the equation of motion? Yeah,
Mass equation.
yeah, that is your basically your yeah. So where is your okay? Now I go back and write rho into x coefficient du by dt. Okay, so I'll put it as dui by dt. Okay, equal to what is that you get? You basically have tau I, right? Tau x. What is that you have here? Tau xx, right? Go back. I'll show you what we derived. We derive now finally equations. Yeah, these are the ones, right? Equations of motion in terms of stress components. Dou tau xx by dou x. This is the one. Okay. These are the equation of motion. Now come back. Now you know what is your tau xx, tau xy, tau xz, right? In terms of the velocity components, you come and put it here. Okay.
Yes, sir.
Those things, if you come and put it here, you will get your Navier-Stokes equations. So I'm just trying to put it in that this notation. Okay. So I'm going to put it as this I notation. Ui means I is there for all I equal to 1, 2, 3. So if you actually put it into that equations, okay, put this. So what is that? Equation of motion now becomes equation of motion. Rho ui equal to minus dou x I. Okay, so xi. That means, okay, why xi did I use xyz? No, so if you want to use here, no, xi, x1, x2, then you have to use x is this one, and x is actually x1, x2, x3. I mean, XYZ you think of as X1, X2, X3 in that notation. Okay, in that notation, if I put it, it is going to be P, this P function, that is actual pressure, plus now you have a 2 by 3 mu minus this lambda. Lambda is there now, both the constants into del dot U bar. Okay, and this is what is this one plus. Now the other one is dou. Okay, so now I have to write summation. Summation J is from 1 to 3. Okay, so dou x j of mu times dou u, basically dou uj by dou xi plus dou ui by dou xj. You understand? Hello? This is what you have to see this one. This is what is exactly, or you replaced your tau xx or whatever the stress components I replaced. Then plus rho into what is that we have earlier? What is the equation of motion? Hello?
So about
Rishabh,
little bit about
you lost, is it? Where is your equation of motion that we derived 3 equations? That's what I'm writing. It's just a notation. Don't worry. Okay. Go back and see slowly. You'll understand this. All are same.
this one.
So we have to write
Yeah.
rho bx. No. So I'll write rho bi. Okay. So I'll put it finally rho bi, where b1, b2, b1, b2, b3 is actually your b vector. Okay. What is this one? External force. External force per unit mass. That's all. So this is your Navier-Stokes equation actually. Okay. Now we'll try to. Okay. So what happens to these constants? Mu and lambda are constants, viscosity constants. Okay. Viscosity constants. So mu is actually the originally your based on. Suppose you have a fluid having a viscosity, that is your mu. But lambda is empirical lambda. So okay, this lambda is something to do. It is because of this delta T. Delta T means what? It is expanding, right? It is basically flux, right? Delta T means what? Divergence. So sometimes there is a, when the fluid is moving, rotating, translation, when this is happening, your fluid element may become big and small. Okay, big and compressed. That is the time this lambda plays a role there. So every time lambda is changing. Okay, you don't know exactly what is that lambda. Lambda is unknown. So that lambda is unknown. If you see here, this lambda is unknown. In that case, how many unknowns are there? First of all, how many equations are here? 3, right? You have 3
Yes, sir.
equations. You have
Yes,
3
sir.
equations. Mass equation is another one. How many total? 4 equations, right?
4 equation. Yes,
How
sir.
many unknowns you are there now? U1, U2, U3.
5 unknowns, sir.
P is unknown. Now delta is unknown.
Yes.
You have 5 unknowns,
Yes, sir.
but you have only 4 equations. Equation of mass equation and these momentum equations 3. So you have only 4. So you need what? You need
Energy equation, sir.
Yeah, you need energy equation. Not U means you. Okay, you need energy equation. Since lambda is unknown. Okay, this is only for compressible fluids, right? Compressible fluids. Why? Delta T plays a role which is not equal to 0 here, right? If delta T is 0, there is no lambda, right? Isn't it? So for incompressible fluids, delta T is 0. We know, right? This is your equation of mass, right? Implies what is that you get now? Rho into d ui by dt equal to, now see, remove that one. So what do you get? So this whole thing is removed, minus dp by dxj. Okay. So what happens to minus dp by dxj? That is simply minus dou p by dou xj xi, right? That is xi plus whatever the term that you have, mu. Mu is anyway known, right? So given a fluid, you know mu directly, you can calculate. So if you actually see this one, mu times what do you have there? What is the mu? Now you have to do this one. You need to write what exactly this one. This is actually, you will have to, if you rewrite and see that, it is going to be basically, yeah. What is that one? Okay, let me write it. So dou square uj by IRJ. I think UI.
UJ, sir, you have written earlier UJ.
UJ part somehow it goes, I guess.
So why there is no sigma part, sir?
Huh?
Why here is not any sigma comes, sir?
Because you're trying to use something. So if you write it, okay. So first of all, your equation becomes vector notation if you write it. Okay. So let me write your vector notation first. Okay. So compressible fluids. Let me write whatever I wrote here above. No, so that becomes in vector notation. If you write it, you will understand. In vector notation, the general equation. Okay, so if you write it vector notation, this du bar by dt equal to minus grad p plus 1 by 3 mu plus lambda. Okay, yeah, that is why somewhere you have used this one. So del of del dot v, del dot u bar. Okay, this is u bar. What is del of del dot u bar? Plus, this is what you have done. So if you actually put it in the vector notation, this is what you will get. That's why this 2 by 3 becomes minus lambda becomes 1 by 3 mu. Okay, something like that you are changing. You understand? So this is what will become if you look at the terms now. So if it becomes this one, and finally you will get rho into b bar. So this is what it becomes. Now you look for incompressible. So you assume this one. Okay, so or you just go and see whatever you have written here. For example, here. So this is in the equation of motion for 1 component, 2 component, 3 components. But dou xi, all these things, you try to see, put it as in vector notation. Basically, this is what it becomes. Okay.
So then if consider for incompressible fluid, then all term become 0, only minus gradient p plus rho b bar.
Yeah, that becomes simple. Okay.
Yes,
Incompressible fluids.
Got it. Yes, sir.
For incompressible fluids, just write it. So incompressible fluids, simply you will get dou u by dt equal to grad p, which you already have earlier, right? When the ideal fluids, you already have this term. This becomes 0. So only term that is extra term is simply your usual coefficient of viscosity. This is your Laplace equation on the vector u, velocity vector, plus this is already there now earlier. This you have external force is already there earlier.
Yes, sir.
So
if
this is actually Navier-Stokes. This is the equation.
Sir, I'm saying that if divergence of u is 0, then double gradient of u is not 0. Like, I think it will be also 0, sir. Mu into.
No. It won't be del of del dot del u. This is called this is basically
Yes,
del
sir,
square, right? Del square u is basically it's a vector. It's not scalar. Okay, it won't be 0. So you go back and see this. It won't be 0. Okay. So this is your Navier-Stokes equation. So followed. So it's a simplified equation. So now we just go back. How
Yes,
do we
sir.
how are we going to, in this case I don't need, we have only 4 unknowns, right? In this case u bar unknowns are u bar, three unknowns, p, that's all, right? So you already have 3 equations, 4 equations. 4 unknowns are these things, right? And 4 equations are mass and 3 momentum equations. Here you don't need really energy equation. Energy equation is only required for the compressible fluids, but where this lambda becomes that there is another viscosity constant is coming into picture, so that takes care of that, gives you that becomes unknown there. Okay, so you don't worry about that, but we're not going to look at it. So that is the reason in your, I think, syllabus they don't consider, they don't ask you to derive the energy equation. Okay. Okay, so now how do we solve this one? So this one, to solve this, you need to have, this is your fluid you have here. Whatever the equations you are satisfying, mass equation, momentum equation. On the boundary, ideal fluid, what will happen? Ideal fluid, u bar dot n cap is 0, right? Or given. If it is a solid, it is 0, right? For solid boundary. Isn't it? So right now for this is for ideal fluids. Real fluids, that means basically you are giving the slip condition. Okay. Okay, but what happens to the parallel to this velocity parallel to the boundary, which you assume to be non-zero? It is just moving. Okay, even very close to the boundary also it is just moving. Horizontal velocities are, you are not considering as zero. But real fluids, no slip condition, no slip boundary conditions. That is all u bar equal to 0 at boundary. Normal also, right? So u bar dot n cap is 0. Okay, so this along with this, you also have no slip condition, means u is 0. It's not slipping. Okay, so u is also, so horizontal velocities, u bar dot tangential. So if we call this tangential, what do you call? So let's call this t cap. T cap equal to 0 and u bar, anyway, along with this you both have. Okay, so these are boundary conditions for real fluids. These are no slip condition, you call this, where t cap is tangent to the boundary. If this is your omega, delta omega is this, to delta omega I'll put it. Okay, that is the boundary. You understand? So along with that, you also have, you see, not just these boundary conditions, you also have, what are the boundary conditions you have? See, this is your only velocities, right? You also have, if you need to consider the stress tensor also must be everywhere continuous. Okay, so you need to consider both the velocities and stress components. Everything needs to be continuous. Hello, one thing la. The 5 minutes office. Okay, I will stop here. Rishabh, you have any doubts?
Okay. No, sir. I will revise if I have. I will ask.
Yeah, I'll
you.
just check it. I'll share it. Maybe tomorrow I will share it because I need to rush. Okay.
Okay, sir. Sure, sir.
So that whatever I just followed that sixth equation that I shared, you know, sixth
Yes, sir.
equation of motion. So that only I followed. Just
Okay,
go
sir.
through it. So you need to, if at all you don't understand, is there is only one thing here. So what is that one? That dou x, that the vector notation to that is the only thing which you miss. You need to, okay. So that is the
Okay,
only
sir.
thing you might not have followed. So that you can easily find out. Okay, that is not a big thing.
Okay, sir.
So any other questions? So I'll come and see tomorrow. Okay, so that book I will tell you. I'll give you information about it maybe tomorrow. Okay, I
Okay.
need to run now.
Okay,
Okay?
okay. Okay, sir.
I'll just drop here and I'll go. Okay.
Okay, sir.